This is our, I think, second to last video, most likely, on an important carbon-carbon bond forming reaction, the Wittig reaction. So I'm going to have this video posted, so I urge you to mostly read through some of this stuff at the beginning in the interest of time. The net reaction is surprising if you take a look. We have a nucleophilic addition to a carbonyl, so it fits with what we've been covering. But notice the carbonyl carbon, labeled 1, ends up double bonded to the carbon I labeled 2. So quite an amazing outcome. But a new carbon-carbon bond, a double bond. The nucleophile is unique and looks a lot different from what we have worked with so far. And this is it right here. But don't be intimidated by this. Notice it's still a carbon nucleophile, negatively charged carbon, with this phosphorus and 3 large phenyl groups coming along for the ride. But they're not just coming along for the ride, they play a key role. You can abbreviate that structure like this. And if we react that with a simple ketone like acetone, common solvent, right? Our electron arrow pushing will be the carbon nucleophile coming in, forming a bond to the carbonyl carbon and kicking those electrons up. Nothing new at all about that, right? The triphenyl phosphorus part is coming along, still attached. And so that ends up with the new bond formed here, as we see, and the formal charge on oxygen being negative now makes perfect sense that you would have internally this bond quickly forming right here, resulting in a 4-membered ring. The breaking of that 4-membered ring is the unique part of this reaction. I think it might have even surprised the discoverers. These electrons will fold in this direction and these in this direction. Actually, there's an alternate way to get to the same result. But notice these electrons will contribute to the formation of the double bond here, while these contribute to the formation of a double bond between phosphorus and oxygen, which is a really strong bond, actually, and that helps the energetics of the reaction driving toward completion, the formation of a strong bond. So the main thing is we have our new carbon-carbon double bond, and with these exact same reactants and product, you can take a look at this video. So play that. I'm just going to go through it once. Here comes, this part is the formation of the ylide, but now here comes the acetone. Here's the acetone forming a bond to the carbon, and the phosphorus coming back and forming a bond to the red oxygen, and then the big triphenyl phosphorus group breaking off, with the result at the end that you have the alkene product. So since you're watching this as a video, you can replay that as many times as you want, but convince yourself that you're seeing the same thing as I've drawn here, with oxygen in red, phosphorus in yellow. Couple of key points. Ylides are resonance stabilized, so here's our ylide that we've been using. It's kind of easier to see how this reacts because it's got the carbon negative charge, but resonance structure can be drawn, and this is a great resonance contributor, right? You're going from no charges to no charges. So ylides are pretty stable. Actually, you can buy instant ylide in a bottle. It's stable. Has to be, I think, kept in the freezer actually, but it's sold and packaged in a bottle. So very stable. So why the Nobel Prize? Well, it's important to be able to form new carbon-carbon bonds, but if you think about this Wittig reaction, you can vary A, B, C, and D groups almost any way you want. There's an infinite variety, and those will end up arranged in the product like so. So any reaction, not only a carbon-carbon bond forming reaction, but any reaction that versatile, that's plug and play, as we say, is pretty important. So well-deserved award. once you understand the mechanism, the only real challenge is to keep track of where and what A, B, C, and D are, right? So come up with a system. I like to number carbons. Anything you can do to keep track of those. In this example, we have the ylide and carbonyl compound. It's going to start out the same way. You'll have those intermediate steps in here where the four-membered ring forms and then breaks apart, and you get your alkene product. So it's real important to remember, anytime you form an alkene, what can happen? You can have E and Z isomers. I think you actually will, in this reaction, have E and Z isomers. There's rotation. Well, really the E and Z is introduced at this first step here. Not really. It's at that first step, there's still free rotation. Then it gets locked in place with the four-membered ring, as we saw earlier. So E and Z might not be in equal proportions all the time. Now, if you take a look at this molecule here, let's bring it down and plug it into here. In this case, either A or B or C or D is slightly different. It's got these extra pieces on. This molecule is vitamin A. So this was a famous application of the Wittig reaction, the synthesis of vitamin A. Okay, so I'll just go through one more full example. Here's a ketone. Here's our ylide. Bond forming. Pushes those electrons up there. These electrons implied, right? You don't have to keep drawing them if you know they're there. Synthetic chemists know what this means without the little dots every time, right? So, then you have the formation of the four-membered ring. You have the electron arrow pushing that gets you to the double bond. I mean, either way, you just have to pull either this bond or this bond electrons over, because you know a double bond forms between those two carbons, right? Then the other one's easy to remember. There's our new carbon-carbon double bond. You know, if you think about, if you had a couple of methyls down in these positions, you have a reindeer. So, a very small one. So, with enough practice in the forward direction of these reactions, you should be able to see that any alkene almost can be made using the Wittig reaction. Here's an alkene in the molecule limonene, right? It's in lemons and limes. And you can imagine this alkene having formed with a carbonyl on one side and an ylide on the other side. In fact, you could have the ylide on this side and the carbonyl on this side. You can have them on either side. There might be a reason for putting them one side or another if you dial into the details, but so this is what we call in synthetic chemistry a retrosynthetic analysis. Chemists don't move from left to right forward direction to the product. Chemists have a product, usually a natural product, that they have to make. And so they're going backwards from the product that they have to make to what they make it from. We haven't been doing that way at all, you know. So, but the first thing is to learn the reaction in the forward direction. Notice here's a carbonyl compound and an ylide. And again, you can put these, you can switch these and you end up with the same thing again, right? So get comfortable with that. There's some homework problems geared toward that in McMurray, I believe. I think it's that homework problem. This one relates to vitamin A. The McMurray reading is short. The Klein reading, again, in this case, I think is much better. And there's some more and better, well, equally good problems in Klein.